Greetings and salutations, magical chemists. Let's go ahead and jump right into our whirlwind review of atomic structure, starting, of course, with Coulombs Law. I'm sure you remember Coulombs Law. It's that fundamental relationship between electrostatic attraction and repulsion. It applies to lots of things like charged particles or magnets, even gravitation. But in chemistry, of course, we're most interested in the energy of attraction and repulsion between subatomic particles. So Coulomb's law is not on the formula chart, but it's okay because you don't actually have to know the formula. You just have to know the basic relationships. It says the energy is directly proportional to the charges of your particles, which is the Q1 and Q2, and inversely proportional to the distance between the charges, which is of course on the bottom. So what this means is your energy of attraction, if they're opposite charges, or energy of repulsion, if they're the same charge, is going to go up. It is going to get bigger as the magnitude of your charges gets bigger. If you have more positives, your negatives are going to be more attracted to it. If you have more positives, your positives are going to be more repulsed by it. Now, it is the opposite for distance, because even though positives and negatives are attracted to each other, opposite would go the other way. Even though positives and negatives are attracted to each other, as you increase the distance, as the distance goes up, their attraction decreases. So the farther apart they are, the less attracted they are. So here's a thought question for you. Which would an electron be more attracted to? The nucleus of a hydrogen atom or a helium atom? All right, so you're going to try this, and when you're ready to check the answer, unpause the video. So hopefully you see that helium would indeed be more attractive to an electron than hydrogen, because the two protons with their two positive charge in its nucleus are going to be more attracted to that negative than just the one positive charge. All right, so let's try some multiple choice practice to see what you know about Coulomb's law. Okay, there are five multiple choice, and you are going to try them all because, just that much fun. And then we're going to check the answers in class. So try it, see what you think, and we will go over it in class. When you are done with those 5 multiple choice problems, unpause the video, and you'll be ready to learn even more about atomic structure. All right, so now that we know the basics of Coulomb's law, let's talk about how an atom is actually structured. Of course, it's divided into 2 regions, the nucleus, the center, which is very, 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 very small, and it has a positive charge. The nucleus, of course, contains 2 very important things, protons and neutrons. Protons, of course, are positively charged particles. They have a charge of +1, and their mass is defined as being 1 AMU, or atomic mass unit, each. The number of protons is defined to be the atomic number, and that's what distinguishes one element from another element. Neutrons, of course, have no charge. They are neutral, like their name suggests, but they still do have a mass of 1 AMU. Remember that AMU stands for atomic mass unit. We use those so we don't have to talk about 1 times 10 to the negative something really, really tiny for grams or something. Okay, so that's the nucleus. Let's talk electrons, which are, of course, in the electron cloud. Electrons are our negatively charged particles, but, they don't have a 0 mass, but it's about 0. The analogy I've always heard is that if a proton was the size and the mass of a bowling ball, an electron would be like a little fly comes and lands on it. It's not that the fly doesn't have a mass, it does, but it's so much less, it's negligible. It's like our X approximation. So, the idea is that if you have something electrically neutral, an atom that is not positive and not negative, it must have an equal number of protons and electrons, so the charges cancel. Because electrons are so tiny, and electron cloud is so huge, it's actually mostly empty space. Crazy, but true. Now, the actual specific regions in space the electrons are found in are called orbitals, and we will go more into those shortly. But before we dive on into electrons, let's talk isotopes, because it's been a little while, and isotopes are important. Isotopes, you may recall, are atoms of the same element, but they have different masses, which means they have the same number of protons, but different number of neutrons. if you want to find the mass of an individual isotope, you cannot look at the periodic table. That's an average mass, a weighted mass of all the isotopes. You just have to take the number of protons and add it to the number of neutrons in that specific isotope. There are, of course, two different notations that we use for describing which isotope we have. The first one is hyphen notation. So like carbon-12. It's literally just got a hyphen in it, right? Because it's the name of the element, and then after the hyphen is the mass. There's also isotope notation, which is what we use when we're balancing our nuclear reactions. Sadly, not AP tested. But this time you just use the symbol, so C for carbon, and you put the mass on top and the atomic number on the bottom. So it's got a little bit more information than the hyphen notation. All right, let's go ahead and try some practice. So our very first example here is given the element carbon, and then we have the mass of 13, atomic number of 6. So first, we want to put that in hyphen notation. Well, if they give you the isotope notation, that's easy, right? Because this is just going to be carbon-13. Because C, of course, is carbon, and it has a mass of 13. The atomic number isn't given. The reasoning is that if they don't tell you the atomic number, you can just go look it up from the periodic table. So now, whoops, that's not a highlighter. It's easy enough to fill out the rest of the chart. The mass number, of course, is given to you in either of the notations. They have to give you the mass number because that's the unknown quantity for an isotope. Carbon-13, of course, has a mass of 13. Now, the atomic number in isotope notation was given to you. That was the number at the bottom, so it is 6. And of course, atomic number is defined to be the number of protons. So if you know one, you know the other. Now, to find the neutrons, all you have to do is take the mass. Because remember, the mass is equal to protons plus neutrons. So if you take the mass minus the protons, that's how you're going to get the neutrons. So of course, if you have a mass of 13 and you have 6 protons, you sure as heck better have 7 neutrons. And because it is electrically neutral, we will have the same number of electrons as protons. So carbon, without a charge, has 6 electrons. All right, so I am sure this is stuff you've seen before, even in this class. So you guys are going to go ahead and fill out these last 2 columns, and then we will check them together in class. Let's move onward and upward. So whenever you are done filling out those last 2 rows, go ahead and unpause the video, and we'll talk about average atomic mass calculations. Yum! Average atomic mass calculations are things that we've already looked at, but it was way back at the beginning of the year, and since we're talking about atomic structure, it's good to make sure we remember. Well, first, if we're going to talk about average atomic mass, we need to talk about how we're actually going to get to the average atomic mass. What laboratory technique? And it is called mass spectrometry. Well, in mass spectrometry, you basically have a mass spec machine, and you put in a sample, and it will separate the particles according to the mass, producing a mass spectrum. So an example mass spectrum is one for silver right here. So notice the peaks, the location of the peaks, are going to tell you the mass of each isotope. So every peak is a different isotope. And the location of the peak tells you the mass of that isotope. Now the intensity, which is the height of the peak, indicates what is called the relative abundance of that particular isotope. That's just a fancy way of saying how common that isotope is in nature. The more of it is, the greater its percent abundance. So you will need to be able to do a couple of different types of calculations here. First, if we give you the percent abundances, either from a mass spectrum or just because we told you, you have to be able to calculate the average atomic mass. Or if we give you the average atomic mass, you have to be able to go backwards and figure out the percent abundance or the mass, whatever you don't have. So let's go ahead and just review how that math works. So a weighted average is just like how your grade is calculated. You don't just add up your grades for the tests and the quiz and the lab and divide them by 3 and be done. No, each one has a different weight. They're more strongly weighted in some categories. Tests more, quizzes less, and so on. Well, the way that the mass is weighted is it's weighted by the percent abundance. The more common it is in nature, the more heavily it factors in to the average mass. So all you have to do is take the mass of each isotope and multiply it by the percent abundance, but the percent abundance as a decimal form. So if it's in a percent sign, don't forget to divide it by 100. But the math is really straightforward. It is important to recognize, especially for those lovely multiple choice problems, of course your average atomic mass has to be somewhere between the mass of the largest and the mass of the smallest isotope. And usually, the average atomic mass will be closest to the most abundant isotope. Now, technically, masses of a proton and neutron are not exactly 1 AMU. We often will pretend they are, but some of the mass is actually converted to energy because there's a nuclear binding energy that actually holds the nucleus together, because otherwise all those protons would repel each other, but they're really close together. So the actual mass of an isotope is not a whole number. Like carbon-13, its exact mass isn't 13. It's probably something like 12.9998 or something close, but not exactly that. So the thing is, if they only give you the rounded whole number values, great, use the rounded whole number values. But if they give you specific, not pretty numbers, use the specific, not pretty numbers. All right, let's try a couple of practice problems, and then you'll be done with this video. Look at that. So first, if you are given a mass spectrum, you need to be able to calculate the average atomic mass from that spectrum. I need you to be careful here, because this is an example of what we call a non-normalized curve. If it was normal or normalized, when you add up all the percentages in something, as a total, it should add up to 100%. But that's not how mass spec data works. They set the height of the highest peak, the greatest intensity, to be 100, and everybody else is a fraction of that. So when you're calculating your average atomic mass, you have to do a little bit more work than normal, but not too much. So of course, if you remember the math, and the equation's right up above you, you just take the mass of each isotope. So the first isotope had a mass of 85. And then you multiply that. You just take its percent abundance on the top. And this one was set as 100% abundance. Now, normally, we would divide by 100. But if you divide it by 100 here, you would be thinking that the 85 mass isotope is the only isotope that exists. And it's not. So to quote-unquote normalize the curve, what we have to do is divide by the total of all the percentages, which, well, 100 plus 40. It's just 140%. So to normalize this, to find its actual percentage out of 100, you have to take 100 and divide by 140. That, of course, is just the first isotope, so we have to do the same thing for the second one. And then you do math, and of course, you don't round to sig figs to the end. Sig figs on this are kind of an interesting question. So if you do the math and you just keep, a calculator answer, you get something like 85.5714, yada, yada, yada. But, and this, of course, AMUs. But when we're talking sig figs, which is why these are usually multiple choice questions, not free response, if you're talking sig figs, technically, you only have 2 sig figs here. So when you multiply this, you only get to keep 2 sig figs. So then with 2 sig figs, you have to look at place value. And with the place value, that unfortunately only rounds to the one's place value. So with sig figs, your answer is 86. Ew. Now, I kept the calculator answer because honestly, the calculator answer is helpful when you're trying to figure out what element it is. Because if this, or, kind of this, is your average atomic mass, all you have to do is go to the periodic table to identify what element that is. And so if you peruse your periodic table, you will see that the glorious rubidium has an average atomic mass that is closest to that, 85.47. It's not exactly the same, it doesn't even round up to 86, but it is closer to 86 than any of the other stuff, and it's definitely closer to 85.57 than anything else. So this must be rubidium. Of course, the average atomic mass in the periodic table includes all the isotopes. Right now, we're just looking at the 2 main isotopes, so that's why our calculation gets an answer that's a little bit different. So whenever you're trying to identify your element, you just go back to the periodic table. Of course, of course. All right, let's try just one more mathy problem. It'll be delicious. Because of course this is AP, we can throw a pretty solid amount of math at you. Nothing beyond Algebra 2, no calculus yet, but we do indeed occasionally have to use a system of equations to solve. So let's take a look at a problem where a system of equations will totally help you out. So in this case, there are 2 isotopes of calcium, and it gives you both the rounded mass and the precise mass, so we're going to use the precise mass. And it says, use the average atomic mass from the periodic table, and then calculate the percent abundance of each isotope. Well, if we write this out as a math equation, we can use our average mass of the periodic table and use the first mass of the isotope times its percent abundance, which I don't know, so I'm going to call it X. And then I'm going to use the plus the mass of the second isotope times its percent abundance, which I'm going to call Y. But we have two different unknowns. Can't solve this yet. But the thing is, there's a relationship between X and Y that we can use so that we can basically make this solvable. What you have to recognize here is that when you take your percent abundances, the percent abundance of the first one plus the percent abundance of the second one has to be 100%. But remember, we're actually using all of our percentages divided by 100. So that means if we take the percent abundance of our calcium 40, we call that our X, and we add it to the percent abundance of our calcium 46, which we're going to call Y. But remember, everything divided by 100, when I add them together, they're just going to equal 1, which means I can substitute in for Y, because Y is just 1 minus X. So now I'm just going to get rid of Y altogether. And if I replace it with 1 minus X, now I have a problem that I can solve with a lot of piles of algebra. Don't forget to distribute your 45.95 and then solve for X. So this is algebra, so I'm going to totally let you do that. It's amazing. But I am going to give you an answer so you can check, because we need this number at the end. So first, go ahead and try to solve this, do delicious algebra, and then when you're ready to check your answer, unpause the video. All right, if you've got X is equal to 0.980, yum, algebra worked for you. Now, of course, that's not our final answer because we wanted the percentages. So that means that the percent abundance, now remember that we said X being the percent abundance of calcium 40. So that must mean this one is going to be 98.0%. But of course, that's only one of them. But if you add them together, they had to be 100. So that means the other one has to just be 2% abundant. So with lots of delicious algebra, we have our answer. But now we can use this information. We can go further. And we can now say, because, okay, in our next question it says, that's great. How many atoms of calcium 46 specifically would be in a 25-gram sample of naturally occurring calcium? Well, there are two parts to this problem. First, you just need to figure out how many atoms total of calcium would be, because only a small percentage of those are actually going to be calcium 46 atoms. So we're going to start off with dimensional analysis, everyone's best friend, and convert our 25 grams of calcium into atoms of calcium. So we just use our molar mass to convert to moles of calcium and then Avogadro's number to find atoms. But we are not done. Remember, if that's all of the atoms of calcium, only a mere 2% of those are actually calcium 46, the one we're looking for. So we just need to add one tiny little calculation at the end. We just need to multiply this by 2%, which just means 0.020, because remember, that's 2% out of 100. So that's it, dimensional analysis with a tiny bit of a twist. And that's how you will get a delicious number of calcium 46 atoms. And there you have it. Worry not, you do not have to do the rest of the problems on this page. We will work on them in class. So you are done with this video, as long as you did the practice problems along the way, and you are ready to move on to the most glorious part of all of chemistry, electrons. I'll see you there.